All right. I would like to begin by thanking the organizers for first organizing this wonderful meeting and then giving me the opportunity to share some of our recent work with you. So Srini began by giving us a wonderful overview of the big big problems in turbulence. I will not worry about turbulence in single fluids. I will look at multi-phase flows. And then we'll see how far we can go along this route. So I'd like to begin with acknowledgements. A lot of this work has been done over several years with mathematical inputs from John Gibbon. Nadia has done a lot of the work I'll talk about today is in the audience. Kiran has done some work on active systems. Prasad, Noirita, Anupam, and Dario Vincenzi. And support, I don't know, this is somehow this thing is the support from various funding agencies. We've written several papers. You don't have to look at them. This is just so that if you need to, you can refer to them later. Here's an outline of my talk. I'll begin with an introduction. Then I will tell you about the generalized Cahn-Hilliard-Navier-Stokes equations for binary, ternary, and active fluid flows. Then I will give you some illustrative results from numerical simulations. Since regularity criteria came up earlier today, I will talk about a regularity criterion for the three-dimensional Cahn-Hilliard-Navier-Stokes equations, some conclusions, and then comments for field theories and field theories. So multi-phase flows abound in nature. I mean, most flows might well be multi-phase. For example, here is a cloud which has got raindrops inside it and so on. There's a real photograph and a schematic. And then, for example, droplets in oil. These are bubbles in a turbulent flow. This is from the Twente group, I think. And this is a wonderful object called an antibubble. This photograph given to me by Gerard Kalelkar. These comprise a shell of low-density fluid inside a high-density fluid, and it's sort of the bottom thins in time under gravity. The ternary fluid examples here is a compound droplet which is used for modeling white blood cells. Here is a bubble passing through a liquid-liquid interface, and then a Faraday instability on a floating droplet. So I've just given you a few examples. And multi-phase flows are very important, and there are several review articles on them. And if you read them, you will find that multi-phase flows mean different things to different people. So here is a very important overview article by Balachandar and Eaton. It says, dispersed multi-phase flows are distinguished from other kinds of multi-phase flows, such as free surface flows. In dispersed multi-phase flows, the evolution of the interface between the phases is considered of secondary importance. Processes such as droplet or bubble breakup and agglomeration do indeed alter the interface between the phases. However, in the context of dispersed multi-phase flows, one accounts for the interface between the dispersed and carrier phases in terms of particle size spectra without considering the detailed evolution of the interface. The sorts of multi-phase flows that I will look at are just the opposite. So we will restrict ourselves to systems in which the different phases coexist in thermodynamic equilibrium, and where it is necessary to account for the surface tension and the breakup or coalescence of droplets of these phases. And to understand such multi-phase flows, we must, of course, combine theoretical methods from fluid dynamics with those of statistical mechanics. I mean, is there in their paper? Yes, right. It's just quotation. That's why I didn't try to summarize it. Well, I mean, it is, again, it's terminology. In an engineering setting, there's dust in your floor, you call it something. Many people model clouds like that. They don't keep track of the, phase transition and this, etc. So you can't see this very well, but this is a statistical mechanician's view of things. If I have to talk of interfaces and surface tensions, at least I begin with the Ising model, which is a model for magnetism with spins SI plus or minus 1. You can think of those as particles. You can always write plus or minus 1 as 1 and 0 in the so-called lattice gas analogy. Now, you can't solve this model beyond 2 dimensions. So in general, you have to make an approximation. A celebrated approximation is the Curie-Weiss theory, which gives you a variational free energy functional as a function of the magnetization. If you carry out a gradient expansion, you get what is called a Landau-Ginzburg free energy functional, which suffices for equilibrium interfaces, a variety of equilibrium phenomena, if you're not worrying about non-mean field fluctuations. If now you want to study dynamics, where it matters whether or not the order parameter is conserved or not in time, you then get the celebrated Cahn-Hilliard equations written down in 1958. And of course, we all know Navier-Stokes, written down 202 years ago nearly. And to do binary fluid mixtures, you must combine the two. And the resulting equations you get are called the Cahn-Hilliard-Navier-Stokes equations, which were also known in critical phenomena as model H. So if you have a binary fluid mixture, then this mixture, we will always work in critical phenomena language below the transition temperature. We are along the first order boundary along which the A-rich and B-rich phases coexist. And then if you look at it, then they will phase separate. And here is, I'm not playing the movie, but this is just illustrative. Eventually, in equilibrium, you will get one interface separating the blue and the red phases. So now we said that we will describe all this phase separation in terms of one coarse-grained order parameter. And if you're just doing equilibrium, here is the Landau-Ginzburg free energy functional. The V phi is the potential, which is the double well. I will show you a plot in a second, which has minima at plus or minus 1, which are the 2 equilibrium bulk phases. And in between, phi changes continuously as you go from A to B, and the free energy cost for that is in that gradient term. Okay? So you can get the surface tension from there. So here's the potential I told you about. And if you want to study the equilibrium interface and you say that it is varying only in one direction, which I call y here, the functional derivative, this minimization, leads to a second order differential equation, which you can solve easily subject to these boundary conditions. So you have A-rich on the left and B-rich on the right. So this is a single interface. Now, of course, you have to combine this free energy functional along with a fluid. So we got back to Navier-Stokes. You've seen all these important terms here. We're only looking at incompressible flows. And here is the equation for the scalar order parameter phi. So you can see that it is advected by the velocity, and then it has to follow this equation where mu, the chemical potential, can be obtained from a functional derivative of the free energy, the Landau-Ginzburg free energy with respect to phi. And this is how the scalar acts back on the velocity field. And I have included both gravity and friction, which can be important in different settings. All right. And this also has a bare surface tension. So for a 2 fluid phase flow incompressible, these equations should suffice, just as the Navier-Stokes equations suffice for conventional fluid. This is a diffuse interface model. So some engineers always raise the question, look, if you look at the scales of interfaces in the lab, they're very, very thin. So what are you doing? This is not realistic. But you can take suitable limits, which are discussed in these 2 papers. Because of the lack of time, I will not go into them. but you can get to that limit fairly accurately. And the advantage is that you don't have to enforce boundary conditions on a moving boundary. Okay, the free energy is taking care of everything. The price that you pay is that, of course, you have to keep track of a scalar order parameter phi in addition to the velocity. And well, you have many different dimensionless numbers. There's, of course, Reynolds, there's Peclet, there is Bond, which is comparing gravity with the surface tension. There is Ohnesorge and then capillary. Cahn number is a dimensionless measure of the thickness of the interface. And the Weber number, which we might see later, is inversely proportional to the interfacial tension or surface tension. We can carry out direct numerical simulations. You've heard about this several times. You heard about these in Mark's talk, a pseudospectral method suitably de-aliased. And whatever we can do because we use GPUs and so on. Of course, we cannot attain the sorts of resolutions that Srini talked about, but they will suffice for the models I consider. I'm not showing you every detail, but here I show you a simulation carried out in this paper where we studied a droplet. We chose parameters so that there was only one droplet, and the flow is stirred with some Kolmogorov forcing. And you keep track of the droplet perimeter, which is suitably non-dimensionalized here. Okay, and you see that it is obviously very, very intermittent, and you can characterize that intermittency by calculating an F versus alpha spectrum or a PDF of this deformation parameter. So, and you can study its dependence on the surface tension. When the surface tension is high, you get a more or less circular droplet, and if the surface tension is low, you get an elongated droplet. I should say that in the language of fluid dynamics, this is an active droplet. It affects the flow even as it is affected by the flow. At the moment, I'm not using the word active in the sense of active matter. I'm not showing you here the effect that this droplet has on the energy spectrum, but if I did, you would find signatures very similar to how a polymer in a flow affects the energy spectrum. You get the analog of dissipation reduction, and the energy spectrum changes in what we would normally call the dissipation range. Yeah. Yes, it does. I will give it to you later. I have it in the paper. Yeah, it does. It's reasonable. So it is turbulent. No matter whether you take the droplet scale or any other scale. We normally take the scale which we get out of the spectrum in the usual way, the integral scale and so on. Yeah, I shouldn't just say something. It's between 10 and 100, but it's still turbulent enough that you would agree that it's turbulence. Now, as I told you, in equilibrium, these two fluids would phase separate. Okay. Now, if you put them in a turbulent flow, the turbulence churns them up, and you get something called coarsening arrest. This has been studied in 3 dimensions also. I show you here our study, the 2D study. Okay, and this is in a symmetric binary fluid, but as you churn up the thing by increasing the Reynolds number, then you get smaller and smaller clusters. You can characterize this in many ways. For example, here is a spectrum. I'm not showing you the energy spectrum. This is the spectrum of the scalar. From the spectrum of the scalar, you can extract a length, just basically like we extract an integral scale in Reynolds number for, in conventional fluids with the energy spectrum. And so this sets the scale of the coarsening arrest scale. And you can see that it compares very well with the prediction of what is called the Hinze scale, which basically balances surface tension and inertial forces. And that plot which I'm not explaining in great detail, shows that our direct numerical simulation is in agreement with what is found on the basis of the Hind's scale. All right, so I can show you how the energy spectrum is affected. You can't read everything on that slide, but what is changing as I go from this spectrum to that one is the Weber number, which is the inverse of the surface tension. And as you can see that as the surface tension becomes smaller and smaller, or the Weber number increases, the energy spectrum is changed significantly by the presence of this thing. And you can also extract fluxes if you want to carry out fluxes. All I'm saying is that here we have an active droplet, which is actively advected by the fluid, but in turn it acts back on the fluid, and therefore the energy spectrum and the the scalar spectrum both get changed. And we can characterize, at least numerically, how these changes occur. So this is we've set the forcing so that we have an inverse cascade of energy here. Now, I mentioned this nice object called the anti-bubble. I just wanted to show you, it's so beautiful. This is not very turbulent, it is mildly turbulent. So we start with that anti-bubble, which in this 2D case shows up as a shell. And because of gravity, the south pole sort of thins, and you can actually see the thinning. And this is, as far as I know, the first really full spatiotemporal evolution of this using this Cahn-Hilliard-Navier-Stokes. Any other method you use, you have to break the bubble artificially. For example, if you use volume of fluid, you can do this in 3D too, which we did. And again, you see the thinning of the south pole of the anti-bubble before it bursts and reassembles into a droplet. You can calculate the time it takes to rupture and plot it versus the bond number, and the results are in agreement with what is found experimentally. Now let me tell you about something else, which is all coming out from Cahn-Hilliard-Navier-Stokes. This is interface-induced turbulence melting in a vortex crystal. That's a lot of things, let me tell you. But what I'm trying to tell you is that these interfacial fluctuations can also lead to a type of turbulence that occurs at low Reynolds numbers. So this is the interface analog of what is called elastic turbulence in polymeric fluids with polymer additives, okay? Low Reynolds, yes. Yeah, no, we can do high also, but I'll show you low. So given this scheme, this is the initial condition that Nadia has done this, so he's right here. We start with so many droplets of one phase and the other. If you ask for what the vorticity field is doing, it is doing this. To fluid dynamicists, this is known as a cellular flow. Since I'm a condensed matter person, I often call it a vortex crystal. And then, because of the interfaces, they start fluctuating. I'll show you a movie in a minute. And this ordered array gets destroyed. And you get turbulence. You can characterize it in many ways. And this is what the concentration field is doing. And this is how it works. I hope this will work. So you see it starts like this. And then it's just interfacial fluctuation driven turbulence. This is very low Reynolds number. For the cellular flow, for a fluid, you can compute analytically the exact transition Reynolds number. We are well below that. And this is just given by, interfacial fluctuation. Well, the dimensionless number in this case would be the capillary number. Okay, so I show you two plots. You can't look at all the details, but don't worry. So here, if you look at the total energy of the system, and so I'm showing you two capillary numbers. This is 0.1, I think, and this might be 0.16, something like that. I'll give you the exact numbers if you want. So the transition is not simple. It's not a noisy simple. If you think of it as a phase transition problem, We have studied this for fluids. We've studied it with polymer additives. We are now studying it with this thing. It's a whole sequence of transitions. So often you get what I like to call a spatio-temporal crystal because it oscillates both in space and in time. So here you can see the spatial, and this is oscillating in time, and a Fourier transform then gives you a single peak in the power spectrum. So it's a spatio-temporal crystal. But if you change parameters like the capillary number, you get a disordered time series, you get a broadband spectrum, you have disorder in space. And if you're a solid state physicist, you would take a Fourier transform and look at these peaks in reciprocal space. So these sharp peaks are like Bragg peaks, but here it's disordered, so it's all mushed out, if you like. No. Sorry? Periodic, right? Okay, so it's periodic. Here it's periodic. In some others, we have hard boundary conditions. Now, I don't know how I'm doing for time. Look here. Yeah, fine, good. Okay. Now I'm going to change the model on you again. Active turbulence. This is a field which is, become very popular. This here, the word active is used not in the sense of an active fluid in fluid dynamics, but with activity, where something is pumping in energy at all scales into the problem. So here again, you know the Cahn-Hilliard thing well, and this is if I had a single scalar. This was first introduced as a model called active model H by the group of Michael Cates. So there is a scalar field psi, which is keeping track of the active microswimmers. And these are the set of equations. The principal difference is that this coefficient here, zeta, is not related to the sigma, which appears in the Landau-Ginzburg free energy functional. It is greater than 0 for extensile swimmers, less than 0 for contractile swimmers. So we will consider the zeta less than 0 case to study turbulence. And again, I showed you the arrest of phase separation by conventional fluid turbulence. I'm showing you here the arrest of the phase separation of the scalar field psi by the self-generated turbulence by this activity parameter. This is at low activity, high activity. So the higher the activity, the more the turbulence. This is how it, So we can again, just like in the fluid case, we could extract a coarsening arrest scale. We can do the same here. Over here, instead of taking this is the scalar spectrum again. And if there were no activity, this arrest scale would increase like in the Lifshitz-Liozov case with the t to the 1/3. But the moment you have activity, it levels off. So the mean value falls as the Reynolds number here. This is an integral scale Reynolds number. So this is up to about 130 or so with the activity. So this is an example of active coarsening arrest. And you can look at spectra, and we will do all the mysterious exponents that Srini talked about. We can add some more. So in this particular case, the energy spectrum is arguably 5/3, but the phi spectrum is also probably 7/6, but we don't know. You can calculate many terms that go into an energy budget equation, which I'm not giving in detail. But I just want to say that, there are a whole class of systems which are enjoying a lot of popularity these days of turbulence in active fluids. And this is one of the simplest ones where you can examine the consequences of that activity. And there is some hope that it actually applies to systems of contractile swimmers, in particular, these types of bacteria, and also some synthetic active colloids. All right. So quickly, ternary fluid flows. What you can do for 2 fluids, you can do for 3 fluids. You just have to keep track of 3 concentrations such that their sum is 1. There are a whole bunch of surface tensions, one for each interface, all right? And this is what the analog of the simple double well potential looks like. Please don't look at details. And then you couple it with the fluid and you get Cahn-Hilliard-Navier-Stokes, but for 3 components. So let me illustrate how well this works for a simple problem, which has actually been investigated experimentally recently. They bring together 2 liquid lenses and a bridge forms. If you have 2 spherical droplets coalescing in the viscous regime, it's t to the 1 and t to the 1/2, where t is time. In the liquid lens case, it is t to the 1, but t to the 2/3. So I will show you how we can study this. We can generate liquid lenses like this. So let me not bore you with details. Perhaps you can see these. These are the liquid lenses coming together. And you see a beautiful vortex quadrupole which forms. This is in the so-called viscous regime. This is in the so-called inertial regime. And the same story goes through in 3 dimensions also. And we can see the full crossover from the so-called viscous regime, where it is t to the 1 to the t to the 2/3 regime in this case. And the Cahn-Hilliard-Navier-Stokes equations are good enough to follow it. You can do it for 3D also, which is shown schematically here. Please don't look at all the details. And the spectra in the so-called viscous regime, there's nothing very interesting, but in the inertial regime, you do get energy spread over several decades in K. And to that extent, it is turbulent. And I think there is no great theory of these spectra. Probably closure might work reasonably well, but we can come back to that later. And there could be, of course, various turbulent analogs of these 3-phase systems. Now, how much time do I have? 12 minutes. Okay. We can actually get a self-propelled droplet. It is so beautiful that I must show it to you. Suppose you have 2 scalar order parameters. Psi is like the active microswimmer that we had in the previous equation with active systems. And then in addition, we have another scalar parameter phi, which is a sort of like oil in water. And psi likes to be inside this phi, okay? So it's like an encapsulated, active swimmers in a droplet, okay? Again, don't look at the details, but you get 2 types of stress terms. And again, we will look at the case for contractile swimmers. And there is an activity parameter which measures the ratio of the coefficient of this term with the conventional surface tension. Okay, if you do that, at low activity, you get conventional phase separation in a circular domain. It's well known from decades ago that this phase separation occurs by the formation of rings which coarsen and coarsen. But I want you to look at this particular one, where as we increase activity, we get a droplet propagating rectilinearly, all right? But if we increase it too much, then of course it becomes a sort of jiggling droplet because of turbulence inside the droplet. And all this happens because if you look at the flow field, initially there is a vortex quadrupole, but eventually it gives up and a vortex dipole forms, and that's what propels this droplet in that direction. Okay, I think there is, I will show you a movie much later. And if you keep track of the center of mass of the droplet, okay, in the region where it is going rectilinearly, it's straight, but otherwise it's very jiggly. And by plots of, say, mean square displacement, you can see a crossover from ballistic motion to diffusive. But in between, there seems to be a distinct region where you could argue that it might be a lady walk, but with a fully active droplet, it is hard to get very good statistics to prove that conclusively. Again, you can look at the interface fluctuations in the case where it is turbulent, and sure enough, they're multifractal. I showed you this for a conventional fluid and a conventional droplet, and you can again get a multifractal, spectrum for it numerically. Okay, so I've shown you by illustrative examples that the Cahn-Hilliard-Navier-Stokes set of equations is very good for looking at several multi-phase flows. Let me end with two minor remarks. One was about the regularity of such equations that came up in the Navier-Stokes and Euler context earlier. So as you know, this is an open problem for Euler, Navier-Stokes, etc. Various results are known in 2D, but in 3D, it is quite challenging. Okay, I should tell you that for Euler, the celebrated equation theorem is that due to Biel, Kato, and Maida. See, when you look at singularities, you might think, oh, I have to worry about the 257th derivative of some field. The great thing about this theorem is that it tells you the only object you need to look at is the L infinity norm of the vorticity, and you integrate it up to time t star. If that doesn't blow up, then everything is fine, and you don't need to check any other field, right? And if not, then you have a finite time singularity. So, okay, let me down to Navier-Stokes, what is known, what is sufficient, it's still unsolved. But what we did with John Gibbon was to come up with a BKM-like theorem for regularity of this Cahn-Hilliard-Navier-Stokes equations. So there we had an omega infinity, which decided whether or not there is a singularity or not. Here we have E infinity, and E infinity here is just the L infinity norm of what we had in the free energy functional plus what you get for the fluid. And you can see that in most of the things we tried two sets. I'm just showing you one, which was sort of Rayleigh-Taylor case. You, instead of computing E infinity directly, which is hard, you can compute the LM norms, and then they stack up, and they seem to be approaching a limit. And so for all the things we studied, this was well defined. So we hope that Cahn-Hilliard-Navier-Stokes is also not singular. But if we have to decide, here is a criterion, which is the analog of the BKM criterion for fluid. So I end with just one set of talks, a list of things to do. Since this is a field theory and turbulence meeting, I thought field theorists should also look at multi-phase turbulence. And, there's a lot of, in the old days, Jachot and Orszag started something with randomly stirred Navier-Stokes equations. So I showed you various different types of turbulence that can emerge from the Cahn-Hilliard-Navier-Stokes equations. Can you come up with things like that? And there is some work which goes back to a student of Jointo's. But they all worked in what I would call the high temperature phase, where the fluids mix. So I don't know how far one can go. One should try. I also should mention that most of these calculations, which were done with these randomly forced models, A, I think never got multiscaling. B, never accounted properly for sweeping divergences, which were mentioned earlier. And you have to be very careful in 2D because of inverse cascades. And of course, there is a whole bunch of models when you start looking at activity-induced turbulence, and Jointo and Kirkpatrick have been looking at this using these randomly forced models with all the caveats that I have mentioned. So I thank you for your attention, and I'll be happy to answer any questions that you have.
Does this active scalar case, does it have much to do with, let's say, something like the central part of the thermal convection, for instance, where the boundary conditions not so influenced by the walls, but they would be sort of similar to a box that you are.
Okay, I must confess, I've never thought of convection as an example of active turbulence. Because
it is, of course, but
active in the sense, the way these activity people use the word, it is pumped in at, but it's certainly an active fluid. So I wish they had not picked the word active, even though many of my friends were involved in naming that field. But an active fluid to a fluid dynamicist means the fluid affects the other thing, etc. Right, yes. So here, but they all, one word is being made to do the job of two words.
Are there further questions? So let's thank the speaker for the nice talk.